Hello, it's Dave Giles here for the next lesson of IGCSE Physics, Cambridge International Education, Unit P1, Forces, Motion and Energy. And today we're looking at velocity time graphs. So our learning objective for today are to describe how gradient affects acceleration in a velocity time graph, calculate acceleration from a velocity time graph, and apply mathematical knowledge to determine displacement from a velocity time graph as well. So here is a rough velocity time graph. Now, I've used velocity, speed would be very, very similar, but we're going to talk about mainly velocity. So horizontal across here, that just means constant velocity. Diagonally up in a straight line, I should say, is constant acceleration. Diagonally down, which we've got here, is constant deceleration. And the gradient is the acceleration or deceleration of the object. The steeper the gradient, the bigger the acceleration. I will also add that if you get a negative gradient, that means deceleration. And the area under the graph is the displacement of the object. So, very simple graph here first. Describe this journey. Well, we can see the velocity is constant at 4 meters per second. And we can work out the displacement by just doing it's a rectangle, so 10 times 4 is 40 meters traveled. Very straightforward. The next one here is an object which is accelerating. So we'll work out the acceleration here. So it's the gradient change in y divided by change in x. So I've drawn my triangle. The change in y is 10 meters per second. The change in x is 4 seconds. So the acceleration is 10 over 4, or 2.5 meters per second squared. So we're going to calculate, look at a graph where the motion isn't constant. So for the first 3 seconds, I've got a ball accelerating here. So we can work out the acceleration by using change in y divided by change in x. So it's 30 meters in change in velocity in 3 seconds, so 10 meters per second squared. The ball then travels at a constant velocity for 1 more second. How far has the ball traveled? So there are different ways you can do this. You can do parallelograms, etc. I generally just split it into different sections. So I'm going to work out the area under the graph. So I'm going to split it into 2 sections. I'm going to call the bit on the left the triangle A and the bit on the right the rectangle B. So it's a triangle, so it's the displacement or the area is half the base times the height. Half times 3 times 30, which is 45 meters in section A. In section B, it's a rectangle, so the displacement is just the base times the height. So it's 1 times 30, which is 30 meters. So the total displacement is 45 meters from section A plus 30 meters from section B, so 75 meters. Now, we'll do one that's a little bit more complicated, probably harder than anything you would get at IGCSE, but if you're comfortable with this, then you should be good with the stuff you get at IGCSE. So I've got a car accelerating for 3 seconds. It's a race car, reaches its maximum speed. It then stays at a constant velocity for 3 seconds. Then it, because that was its maximum speed, then adds a little bit of NOx, but nitrous oxide can accelerate. So it accelerates up to 125 meters per second. Then we can work out the acceleration here by doing change in V by change in T. So 125 minus 75, and it's 1 second, so 50 meters per second squared. It then travels at a steady velocity for 3 seconds. Sees something crash going on ahead, so it slams on the brakes. And again, we can work out the acceleration, or here it'll be negative, so it'll be deceleration. So it's v minus u over t, same as here. So v, the final velocity is 0, minus u, the initial velocity was 125, the time is 2 seconds. So you get negative 62.5 meters per second squared, which means it's decelerating at a rate of 62.5 meters per second squared. Okay. Now, a little bit of a challenge. Pause this. I want you to see if you can work out the total displacement of this car. I'll let you pause it and I'll go through the answer in a minute. Okay, for something like this, you're definitely going to have to split it in different sections. There's different ways you can split it in different sections. I will show you one way, but you should get the same answer no matter which way you do it. So this section here, I'm not going to go through all the formula, but for this one, the triangle, so it's half the base times the height, 112.5 meters. This section here, 225. I'm splitting this into two sections, or I could do it in one. The little triangle here is 25 meters, and this section 75. Rectangle here, 375 meters, and this section 125. Like I say, there are different ways you can, pardon me, there are different ways in which you can split this up, but no matter what, you should get the same answer of 937.5 meters. So let's have a look at some past paper 2 questions. Well, we'll start easy. This one's taken from paper 1. So the speed time graph for a train is shown. Which region of the graph shows the train moving? So it's only the sections where the velocity isn't 0, so that is not moving. So it's only section P where it's not moving. So the answer is therefore Q, R, and S. A speed time graph is, so this is now paper 2, so it's the extended paper. A speed time graph is used to describe the motion of an object. Which quantities are calculated from the gradient of the graph and from the area under the graph? So the gradient of the graph gives us the acceleration. Now, I had only really talked about velocity time graphs, but if we're looking about speed, instead of displacement, it'll be the scalar version of that, which is distance. So the answer is A. The diagram shows speed time graph for 4 different bodies moving for 6 seconds. Which body travels the least distance? So I can see straight away it's not going to be C or D because that's a rectangle and that's only got a small section where it's not moving, a small section which is not covered, sorry. So here, it's a triangle, so it's half the base times the height. It's 3 times 8, so I sit half times 6 times 8 rather. So 24 meters traveled there. Actually, no, I'll go through them all. C, it's going to be 6 times 8, which is 48 meters traveled. So it's not going to be that one. Here, split into 2 sections, so it'll be 4 times 8, which is 32, plus 2 times 4, which is 8, so 40 meters. So B, let's have a look at this. Triangle first. So a half times 4 times 8. So that's 16, plus another triangle, a half times 2 times 4, which is 8. So yeah, this one has traveled the least distance total. So the answer is therefore B. Speed time graph for a car. Which row describes the motion of the car at point X and at point Y? So at point X, it's speed. So it's 2 seconds at point X. It's moving with changing speed. It's accelerating, so it's changing. And at Y, it is, if it was down here, then it would be stationary, but it's not. It's already reached the speed, so it is moving at a certain speed. So it is moving with a constant speed. So the answer is therefore D. And the last one, the velocity time graph for a car is shown. What is the distance traveled by the car in 35 seconds? Um, so it's just here we're just going to use distance traveled by the car in 35 seconds. 2 seconds. So I'm going to split this in different sections. I'm going to annotate it here. So I will use the pen. I'm going to split it like this. And I'm going to split it like this. So I'm using a mouse on my hand here, so it's not the neatest in the world. So this here is a triangle, half the base. So half 10 is 5 times the height of 10, so that's 50 meters. This is 10 to 35, so that's 25 times 10, which is 250. And this section here is another triangle. So the base is 10, so half the base, half of 10 is 5, times the height of 10 is 50. So add these up, 50, add 250, add 50 is 350. So the answer is therefore B for this one. Okay. And that's it for this lesson. Thank you very much. I will be uploading next lesson soon on resolving vectors with scale models. Thank you very much, and I'll see you in the next lesson. Thank you and bye.